Hello everyone, Dr. Zia Tahir here. This video tutorial is 2D plane truss analysis in Abaqus CAE. This plane truss is a 9-member truss and each member is made up of material having modulus of elasticity 30 gigapascal, Poisson's ratio 0.3, and each member has cross-sectional area of 20 into 10 to the raised power 3 millimeter squared. And the loading 3 loads are being applied at different nodes, and one end support is roller support, the other one is pin support. So required is deflection at each joint of the truss and axial truss in each member. So this is problem 2.2 from chapter 2 bar element from book Introduction to Finite Element Analysis using Abaqus, MATLAB and Abaqus. So this is a book Introduction to Finite Element Analysis using MATLAB and Abaqus, chapter 2 bar element, and it is problem 2.2. So there is problem 2.2 and the solution of this problem is available in the book. So I'll use that solution to compare my results or otherwise to verify Abaqus results. Tutorial is lecture 4 of truss analysis series, and lecture 2, 3 and 1, so they are also 2D plane trusses. So in this video tutorial I'm going to use a different method of sketching. So the basic one I have used in these tutorials. So steps for modeling plane truss analysis in Abaqus. So modeling, analysis and results, and these are the steps, and I'll follow all these steps for the analysis. So first thing, that Abaqus doesn't have any predefined units, so you have to select your own units. So you can either go for Newton meter Pascal, pound inch psi, or Newton millimeter megapascal, or Newton per meter millimeter square. This problem, all lengths are in meters, modulus of elasticity is in Pascal, and area of cross section is in millimeter square, so you need to convert that into meter square. Okay, so you need to change all units either as given in set 1 or in set 2 before start solving a problem in Abaqus. I am using Abaqus CAE 2020, and this is when you open Abaqus, so this is how it looks like. And first you need to set work directory. So work directory is a folder where you want to save your model and all results. So I have here plane truss 9 member. I am just going to copy its address and then file, set work directory, and I'm going to change that. So okay, so now work directory is being set, and then need to save model. I am going to save in the same folder plane truss 9 member, and it is a model database and extension is CAE. So okay, so now the model is being saved. First step in the modeling is to create part, and for truss it is 2D deformable wire, and then approximate size is 2 times the maximum length, and then create lines, connected lines. So here you have there are tabs on the top, tab, and then here you have module, and here is a model tree. So you can create model using part, using module, or using model tree. So click on part, name is a truss, so 2D deformable wire, and approximate size of this must be 2 times the maximum dimension. Maximum dimension, like the maximum length or width of the whole model here is 7.2, so almost 2 times of that is 15. So I can go like 15 or 20, so that is continue, and now you can see a grid in XY plane. Okay, and then you need to sketch. So you can sketch through connected lines or created lines connected, or you can start with created isolated points. So I am going to create isolated points, and then based on that point I'm going to connect lines. So just select here, and that is the first point created. So now the next point, so it says that pick x or y coordinate, and for this node 2, its x coordinate is 2.4 and y coordinate is 1.8. So I'll enter here 2.4 comma 1.8. So you see another connected point is being drawn, and the next one, this point 4 is 4.8 and 3.6. So the other one is 4.8 and 3.6. So in the similar way I can create other points. Now those 6 points are created here. So the next one, I'll select here create line, connected line. So I'll just connect these points. Okay, so here you go, and then vertical members here, cancel procedure, again vertical member there, and then there are some diagonal members joining 3 and 4. So that is the diagonal member, cancel procedure, and now it's done. So once done, so that is here is created. So you can check dimension, and to check dimension you need to go back here, sketch section, and then here you can add dimension to all it. Okay, so done, and you can see that is 2.4, and then all these dimensions. So done. Okay, and you can see that it is being suppressed, so modified. So first suppress it and then resume it. So now first part, like first step, model is being created or it's being sketched. Next step, in using property module, create material, mechanical, elastic, type, isotropic, and need to add modulus of elasticity and Poisson's ratio. So here in the module, I'll click on property. So you can create material from here, you can create material from there, or then you can create material from there. So click on the material, and now material, I'm just naming it as material, and then elasticity, elastic, need to add Young's modulus. So Young's modulus is 30 gigapascal, 30 e raised power 9, E9, and then 0.3. So now you can see that a new material is being created and its name is material. Next step is create section, and category is beam, type is truss, and need to add cross-sectional area, and cross-sectional area should be in meter square, and I'm going to name that section as truss. So it's very simple. Again in the property module, so you can create here section or section create, or otherwise here you have section to create. Okay, so double click here, and then you have section. So I am going to name it as truss. It is a shell, category beam truss, continue, and now you need to add here area of cross section. So area of cross section is 200 e raised power minus 3. So now that section is being created, and you can see that here is a section. So if you want to modify, so you can modify area later. Next step is assign section, and for that need to region, and you need to select sketch and then assign that section as truss. So now here you have assign section, or you have here in section assignment manager, or you can have here section assignment. So I click here section assignment. So it says that select the region to assign a section. So I'm not going to create any set. So with the box selection I'm going to select all that. So done, and now because I have only one section, so that section is being assigned, and after section assignment it turned to green, light green. Next step is to create mesh, and for that seed edge, by number, and then mesh part, and then assign element type. It must be to T2 D2. So again here you can go to mesh module. So that is a mesh module, or otherwise when you go to the mesh module, so this tab is going to change to the mesh, or otherwise you have mesh empty here. So here is seed edges. So seed edge, it says select the region to be assigned local seed. So I am going to select all that. So done, and then method by number, and I'm going to select one element between two nodes, so which is usually used in theory of truss analysis. So apply, and then you can see there are small rectangle appeared there. Apply and OK. So it's done. So seed part is done. So the next one, you need to go here, mesh part, and it says that OK to mesh part, yes. So now it's being part is being meshed, and the next one is need to assign element type. So click there, and it says select the region to assign element type, and then I'm going to select all that. So done, and now here in the family need to select truss, and then it is standard linear, and you can see here type is a two node linear 2D truss. Okay, so and that done. So now mesh is created. Next step is create instance in the assembly module. Create instance from part and then select part. So here I can go for assembly module. Okay, so now in assembly here you have create instance, or you can here instance create, or otherwise in the model tree in the assembly you have here instance. So I click here, so create instance from parts, and then its part is already truss, so I am select OK. So now you can see there, so a truss is being created. So when you click on that, so it is turned to red. Next step is to create step, and procedure type is journal, and then static journal, and I'm going to name that as static load. So it's very simple. I need to go here in the module, step module, and when I'm going to, so here you have create step, or here you have create step, or otherwise here after that assembly you have here step. So click, you can double click on step, so create step and insert new after. So this is initial, procedure type is journal and static journal, and I'm going to name it as static. So that is static load. So continue and leave that everything default. Okay, and you can see step is being created. So I can minimize all these. Okay, so now step is created. Next step is in the step module, modify field output, because only displacement and stresses are required. So I am going to add only displacement and stresses in the solution. So here in step module, so you can create field output, or you can modify already created field output, or otherwise here you can see, go there, here are the field output. So double click on that field output, so you'll have these options. So stresses, strains, I'm not interested in strains, I'm not interested in forces and reaction, and then not contact. So only I need those. There are so many stresses, so I'm just going to select which is default selected, and then the displacement, again there are so many, but I'm just going to go for translation and rotational displacement. So only two stresses and displacements, so they are requested. So I click OK. So now field output is being modified. Next step in the load module, create load, and step is already defined static, and then category mechanical type concentrated force, and then select point where you want to apply load. So a load of 10 kilonewton is being applied at node 2. So I'll here you in module I'll select load, and then here you have create load, or otherwise in the model tree you have load here. So I double click on load. So load 1, and step is static load, mechanical concentrate force continue, and then I'm going to select this point. So done, and now you can see that here you have CF1, CF2, so that is constant force component along x-axis and y-axis. So I have 10 kilonewton along negative, so it is minus 10 E3. Click OK. So you can see that a load is being created, and here you can see a load is being created. Similarly, by clicking here I can create a load. So load 2 is a mechanical constant force continue, and here at node 4 there is another 10 kilonewton load. So I'm going to select this point, so done, and again here minus 10 E3. Okay, so it's that second load is being applied. So now I can go load here and create load, and now this is load 3. Oh, continue. I am going to select this point, and at that point the load is 7.5 kilonewton. Okay, so select the point, so it's done, and now it is in negative x direction. So it's minus 7.5 e raised power minus 3. Okay, so now you can see that 3 loads are being applied. So this is how you can apply concentrated load. Next step, in the load module need to create boundary condition, and step must be initial, category mechanical, type displacement rotation, and select the region where you want to assign boundary condition. Node 1 is a roller sport. So roller sport, on this type of roller sport, it is free to move along x-axis, but it is restricted along y-axis. So I'm going to create a boundary condition here. So now in the load module you have this second option of creating boundary condition, or you can go here BC. So BC, and then create a boundary condition, and here step must be initial, category mechanical, and then type displacement rotation, continue, and now I need to select this point. Point selected, so done, and now it is a roller sport. So for roller sport u1 is not 0, like as there is displacement in x direction but y direction is restricted, and roller sport that it doesn't resist any translational rotational displacement. So okay, so now roller sport is being set there. Now you can see here, so one BC is being created. So I double click on BC, now BC2, and then its initial mechanical displacement rotation, continue, and I'm going to select that point here, and then done here. And now because the pin sport, so I need to put that u1 and u2 both equal to 0, so it's okay. So now 2 boundary conditions are being applied. Next step is to create job. In the job module, create job, rename model, apply data check, and then submit. So here you can go into the load module, module, and is a job. So you can create job here, or here you have job, so you can create job. But before that, I am going to rename that model, and I'm going to rename that as plane, truss plane, also truss plane. I'm going to copy this name. So, and then okay, and now I'm going to create a job here, double click on job, and then its name I'm going to put as truss plane. So continue, and now leave as it is default. Okay, now under the job, so that job is being created. So now I can perform here data check. So data check here submitted. So data check will tell you if there is anything wrong with standard procedure in the modeling. So data check running, and then after some time you can see that data check complete, and then it says that job completed successfully. So once data check is complete, so then you can go for submit. Okay, so it is job submitted. Then after some time it changed status running, and after some time you can see that it's from running. So now job is completed. Here you can see, so that job is completed. It's mean that analysis is done. Now the next step in the results, visualization module, field output dialog, and need to visualize these results. So here module visualization, but before that you need to get results. If you go to results here, so so you can't see anything in the results. So now you need to right click on the job and then you need to go results. Okay, or otherwise file, open, and then you have that ODB file. So click OK and then click OK and then that is the ODB file. So here is deformed, undeformed model. Then you have here deformed model. There is a deformed model with contours, and then here both deformed and undeformed model. By clicking here you can get, and then here is a deflection that is in x direction, deflection in y direction, stresses, and then S11. So that is S11 is in axial direction. So here you can visualize the results, and then you can go to common option and you can add element label and node labels. There you can change it color, element label to black and node label to red, and apply. So now you can see that so they are being displayed, and you can change that viewport background like by going graphic options, and then you can add a gradient top to bottom, apply, or you can go solid. You can change that color in of viewport. Now the next step in the visualization module, you need to probe values by probe nodes, components all, and display group all, and then write file. So first I'll go into the field output dialog here, and I go U and then its component, but I'm going for magnitude. Then go to tools, and then you have query, and then a probe value, and this new window will open. Or otherwise here is the probe values. So you can on that probe values. Okay, so you can go node, component all, select a display group, and then here all, and then so you can see that for each node its first is horizontal deflection, the second one is vertical deflection, so that is given. Okay, and then you can go here write to file, and then with write to file, so you can rename that as report file. So that is simply plain truss, and then number of significant digit you can keep here 6, and number format engineering, and then you can get values. So now okay, so report file is being saved in your work directory. So I double click on it, and then you can see that this is the report file, so that contain all the deflections. Next step in the visualization, S11 for axial stress, probe values, and then probe elements, because deflection is on node and stresses are for elements, and component all direct, display group all, and then write to file. So it's simple now. So it's simple. Here in the field output dialog, I'll go S and then select S11. Now here is a probe. So in the probe, I need to go elements, and then position, you need to select centroid, and then all, and now you have the values. So here are the axial stress results. So like stress in member 1, so that is the member 1, it is 416.667 kilonewton. So here you can see that the same value you got there, 416.667 kilonewton, and then in member 3 it is 5, and here you can see in member 3 is 500,000, and similarly all those results they matches well with the results from the book. And now I can create that. First I need to close that report file, then write to file. I'm going to append to the file, Okay, so click OK, and now here again if I open the same previous file, so now that prob value that is being added, like these are the stresses, so they are being added, and these stresses are exactly matches with the solution. All steps are done and analysis is finished now. Now the summary of this tutorial. So 9-member plane stress is solved in this tutorial to calculate deflection and stress. And these are the 3 steps in Abaqus: modeling, analysis, and results. So need to first set unit, set work directory, save model, then create part, create material, create section, assign section, create mesh, create instance, create step, modify field output, or sometimes you can create field output, then create load, create boundary condition, and then create job, rename the model, data check and submit, and then visualization using field output like dialog, so you can visualize the results. And then to get the exact value, you need to use prob values at nodes, and then you can write to a file. And then similarly for stresses, S11 it is axial stress or member stress, and that you need to use element. So this is all from this tutorial. Thank you very much for watching. I hope you find this tutorial helpful. So you can leave your feedback in comment section.